Running cables and conductors is an essential part of electrical maintenance. As an electrician, you need to know how to select the right combination of conductor, insulation, and hardware necessary to do a job. You also need to know how to install cables and conductors safely and correctly in accordance with your plant's procedures. In this unit, we'll look at cables and conductors. We'll begin by going over some general terms, and then we'll talk about how cables and conductors are classified and how you determine which conductor is right for a particular job. Then we'll look at installation procedures. We'll go over how to install a conductor, how to do a splice, and how to do a termination. In this segment, we're going to take a look at how a typical conductor is constructed, so you'll have an understanding of what conductors do and how they do it. Then we'll take a brief look at how cables are put together. But before we start, let's define conductor and cable to make sure we're all using these terms the same way. A conductor is any material that provides an easy path for the flow of electrical current. Virtually any material will conduct electricity, but some do it better than others. Copper, silver, and aluminum are examples of materials that are good conductors. Of these, copper is the one most commonly used in standard electrical applications, and that's the one we'll use as our example. A cable is two or more conductors insulated from each other, but bound together by a common covering. You may hear single conductors called cable, and you may hear a multi-conductor called cable. But for simplicity's sake, in this lesson, we will use the term conductor to mean a single conductor and the term cable to mean two or more conductors in a common covering. All right, we've defined the terms. Now let's see how a conductor is constructed. Here we've got a bare conductor. Now most conductors can be divided into two categories, bare and insulated. A bare conductor has no insulation around it. It's just a length of metal wire. Conductors in general can be broken down into solid conductors and stranded conductors. A solid conductor is made of a single strand of wire. A stranded conductor is made up of several strands of wire wound together to form a single conductor. Stranded conductors tend to be a lot more flexible. That is, they're a lot easier to manipulate or bend. Although bare conductors have a place in the scheme of things, insulated conductors are used much more often in everyday work. Why? Well, the insulation offers two kinds of protection, mechanical and electrical. Copper is a relatively soft metal. It can be damaged easily, so you want some mechanical protection around the copper to keep it from being damaged. The electrical protection that insulation provides has a lot to do with the fact that copper is such a good conductor. It provides a nice, easy path for current to follow. The insulation's there to keep the current on the path. Insulation materials are by design poor conductors. They offer high resistance to current flow. Materials that fall into the category of poor conductors include glass, rubber, paper, and plastic. To make this an insulated conductor, we have to cover it with a layer of insulating material. Let's cover it with rubber. Rubber won't permit much in the way of current flow. Okay, now we have a conductor insulated with rubber. The rubber gives us the two advantages we mentioned earlier. It keeps current flow within its boundaries and provides mechanical protection from damage like nicks or scrapes. This insulated conductor could be installed in lots of circuits inside the plant. just as it is. But in other applications, out of doors for instance, additional protection might be necessary. In that case, a jacket like this one might be added. It covers the primary insulation. Jackets are commonly made of hard plastic material which provides additional insulating properties and mechanical strength to a conductor. This is called a sheath. It's an additional covering applied over a jacket, mainly to provide extra mechanical protection. When you start working with high voltage installations, you'll find conductors and cables covered with multiple layers of insulating materials that range all the way from organic materials like rubber to complex synthetic materials developed to meet specialized needs. As a rule, though, the additional protection provided by jackets and sheaths is only needed for applications in which the environment or the temperature demands special treatment. Under ordinary circumstances, one insulating material usually provides all the protection a conductor needs. Well, we've seen how a conductor is built, but what about cable? How's it different from a conductor? Well, they don't differ in basic function, but they do differ in design. Let's look inside a cable and you'll see what I mean. Here we have three conductors separated from each other by insulation. So a cable is two or more insulated conductors surrounded by a common covering. The type of insulation around the conductors and around the cable itself is chosen according to the purpose for which the cable is designed. Every manufacturer designs conductors and cables suitable for a range of applications. In the next segment, we're going to talk about how conductors and cables are classified and how they're rated. But before we get into that, why don't you review the material we've just covered in your text? If you have any questions, be sure to ask your instructor about them. You've seen how cables and conductors are constructed, and you have a general idea of the function of each part of a conductor and a cable. The next thing we're going to talk about is how cables and conductors are classified and rated. Their classifications and ratings are closely linked to the size and type of material used in their construction, as you'll see. We'll use a single insulated conductor as our example in this segment, but the facts will pertain to all types of conductors and cables. Cables and conductors are classified according to two things. They're the size of the metal wire in the conductor and the type of insulation surrounding the metal wire. Cables and conductors are rated for two things as well. They're rated for the current carrying capacity of the metal in the conductor and the value of the voltage that the insulation surrounding the metal wire can withstand. Let's go into the subject of classification in a little more detail, and then we'll cover ratings. We've said classification is based on wire size and type of insulation. So we'll start with wire size. Now, there are two different systems used to express the size of a metal wire. One standard system used in industry is the American Wire Gauge, or AWG system. The wire size of most of the cables and conductors you'll be installing will be designated according to the American Wire Gauge system. In this system, each conductor is assigned a number that designates its trade size. By trade size, we mean the standard size that's recognized in the industry. AWG sizes range from number 40 to number 4/0. Here are a couple of commonly used sizes. This is a number 8 AWG. This is a number 4. As you can see, the size 8 is smaller than the 4. This pattern holds true for most of the system. As the number increases, the conductor's actual size decreases. However, once you get up into the 0 sizes, they follow a more natural progression. 1/0 is smaller than 2/0, and so forth up to 4/0. But that's not to say that 4/0 is the largest size conductor available. Once you get beyond size 4/0, you're into another system, the circular mill system. The range of sizes in this system goes from 250,000 circular mills to 2 million circular mills. The size designation for this system is based on the cross-sectional area of the metal wire. This cross-sectional area is measured in circular mils. A circular mil is a circle that has a diameter of 1 mil, or 1/1000th of an inch. In this case, the area is equal in size to 250,000 circles, each having a diameter of 1 mil. So this is a 250,000 circular mil conductor, or as it's usually abbreviated, 250 MCM. MCM stands for 1,000 circular mils. Now, here are some samples of conductors that are sized according to the circular mil system. This is a 400 MCM conductor. This one's a 500 MCM. As you can see, as the circular mil size designation gets larger, so does the conductor. Well, we've covered the two systems that are used to designate conductor sizes, and we've looked at samples of each. Let's take a general look at the second thing classification is based on: types of insulation. The materials used to insulate conductors can be divided into two general categories: organic materials and inorganic materials. Organic insulation consists of materials made from plant or animal fibers like cotton, silk, paper, and rubber. Inorganic insulation consists of materials like glass, porcelain, or plastic. Now, once you get past the general categories of organic versus inorganic materials, you're dealing with a series of letter designations. These designations are assigned to different types of insulation, just as numbers were assigned to conductor sizes in the two systems we just talked about. The letter designation is used to identify the composition of the insulation and its application. Because the composition of modern insulation materials is so complex and their applications so varied, it would be impractical to try to memorize what all the letter designations stand for. So the industry developed charts that contain this information. After you've been on the job for a while, you'll find you do know all the particulars about a number of types by heart. But there'll probably still be occasions when you'll need to refer to a chart. We've included one in the text, and we'll be using it later on in the next segment. Well, we've talked about size and insulation types, and the fact that conductors and cables are classified on the basis of these two things. Let's go on to discuss how they're rated now. We've said that the rating is based on the current carrying ability of the metal wire and the value of the voltage the insulation can withstand. Let's start with the current carrying ability. A conductor's current carrying ability is usually referred to as its ampacity, so we'll use that term from now on. Strictly speaking, the ampacity of a conductor is based on two things: the size of the metal wire and the type of metal the wire is. Now, you'll hear the word ampacity used in at least 2 or 3 different phrases. For instance, you'll hear the phrase maximum ampacity, and you'll hear the phrase allowable ampacity. In addition to those, you'll also run across derated ampacity. Let's talk about maximum ampacity first. The maximum ampacity of a conductor is the maximum amount of current a bare conductor can carry without overheating. You're aware of the fact that when current flows through a conductor, that current meets some resistance, even in the best conducting materials. Energy is required to overcome this resistance. That energy is given off as heat. When the maximum ampacity of the conductor is exceeded, the bare conductor may overheat or melt. Now, when a conductor is insulated, the insulating material dictates to a great extent the amount of the current the conductor can carry. That's because in most cases, insulation will overheat and be damaged before the conductor will. So with this fact in mind, engineers established a maximum operating temperature for conductors covered by specific types of insulation. To determine how much current a specific sized insulated conductor could carry at a specific operating temperature, 2 factors had to be considered. They were the ambient temperature and the internal temperature rise. Ambient temperature is the temperature of the area in which a conductor is installed. But since the ambient temperature changes with the seasons, if not day to day, a standard was established for ambient temperature. That standard is 86 degrees Fahrenheit. The other factor, internal temperature rise, is the amount that the temperature of the conductor rises above ambient temperature when current is flowing through the conductor. The amount of current flow that causes the conductor to reach the maximum operating temperature limit is what's called the allowable ampacity of the insulated conductor. The allowable ampacity of an insulated conductor and its maximum operating temperature limit go hand in hand. Now, all types of insulation don't have the same maximum operating temperature. There are different established maximum operating temperatures for different types of insulation. The internal temperature rise of the insulated conductors that goes with each of the established maximum operating temperatures is going to be different too. The internal temperature rise gets higher as the maximum operating temperature increases, but the standard for ambient temperature is always the same, 86 degrees Fahrenheit. Well, what does this mean in terms of allowable ampacities for insulated conductors? Simply put, it means that the same size conductor will be allowed to carry more current if its insulation has a 167 degree Fahrenheit maximum operating temperature limit than it can if it's got a 140 degree Fahrenheit limit. You see, assuming the standard ambient temperature of 86 degrees Fahrenheit, the internal temperature rise permitted with the 140 degree Fahrenheit limit is 54 degrees Fahrenheit. With 167 degrees Fahrenheit, the allowable internal temperature rise is 81 degrees Fahrenheit. You can increase the allowable ampacity of a conductor by changing, that is, upgrading the type of insulation around it. Well, we've said as much as we need to about insulated conductors' ampacity ratings, for now at least. Let's go on to voltage ratings. A conductor's voltage rating is based on how much voltage can be applied to the insulation without its breaking down, that is, before current will pass through it. Just as there are different maximum operating temperatures, there are different voltage ratings. For example, a particular type of insulation may have 4 different ratings. It may be rated at 250 volts or 600 volts, or 1,000 or 2,000 volts, depending on its thickness. You should always be able to see the voltage rating of a conductor's insulation stamped right on it. And you're going to have to check the rating on the conductor against the operating voltage of the circuitry to be sure the rating is high enough to do the job. There's an additional factor to consider if you're working with AC circuitry. You're probably aware that AC voltage goes from a peak value to 0, then reverses direction and goes back to peak value in the opposite direction. Well, most AC circuits are rated according to the effective voltage, and that's less than the peak value. But when you're installing a conductor, you've got to be sure its insulation is rated to withstand the peak voltage. It's easy enough to be sure. You multiply the effective AC voltage by 1.414. This gives you the peak value of the AC voltage, and that's what you insulate for. Well, we've certainly covered a lot of material in this segment. We've gone over how conductors are classified and how they're rated. In the next segment, we're going to use this information to select a conductor. So why don't you take some time now to review all this material in your text and make sure it's all clear to you. If you have any questions, be sure to ask your instructor about them. Well, we've talked about how cables and conductors are constructed and how they're classified and rated. In this segment, we're going to show you how to put all of that information together so you'll be able to select a conductor for a specific job. When you're selecting a conductor for a job, you're going to need to refer to some charts to give you the information you need. So the first thing we'll do is take a look at these charts to see how they're set up, and then we'll use them. We'll be looking at simplified versions of the charts. Complete charts are provided in your text. There are 3 charts in all. The first one shows allowable ampacities. The second shows insulation types and applications. And the third shows derating correction factors that are used to derate a conductor. Okay, let's begin with the allowable ampacities chart. The first column at the extreme left gives the sizes of conductors. They're listed according to AWG and circular mill sizes. To the right of this column are the ampacities columns. In the last segment, we said that the allowable ampacity of a conductor differs depending on the type and thickness of the insulation around it. At the top of each ampacity column, you can see that there is a specific temperature listed in both degrees Fahrenheit and centigrade. This is the maximum operating temperature for the insulation types listed under this heading. For example, in the first column, under the heading of 140 degrees Fahrenheit, there are 4 types of insulation listed. Types RUW, T, TW, and UF. These insulation types can only be used safely when the maximum operating temperature is 140 degrees Fahrenheit or less. The column to the right of this one gives the insulation types that are designed to operate at a maximum operating temperature of 167 degrees Fahrenheit, and the allowable ampacities given for each conductor insulated with one of these types. The next 2 columns to the right contain the same information, but for 2 other groups of insulation types. Now, all 4 of these columns we've just looked at apply to copper conductors. The remaining 4 columns, which make up the other half of the chart, apply to aluminum or copper-clad aluminum conductors. Up above these columns, there's a general statement on the voltage ratings for these conductors. The chart rates each insulation type at 0 to 2,000 volts. But, as we said in the last segment, you have to check the markings on the specific conductor you're planning to use in order to find out what its insulation is rated for. The general statement here at the top of the chart simply means that the types of insulation listed here can only be used on circuits 2,000 volts or below. It doesn't mean that every conductor listed on this chart will be rated for 2,000 volts. Well, we've seen how the allowable ampacities chart is set up. Let's go on to look at the conductor application and insulation chart. You'll be using this chart to find out whether or not a type of insulation can be used in a specific environment. Let's say you'll be working in a damp location. Well, you'd need to check this chart to see which of the insulation types listed in the allowable ampacities chart could be used in a wet location. The information provided here includes the trade name, letter type, maximum operating temperature, application provisions, and the materials the insulation is made of. Let's focus on one type and see what it says. The trade name for this type is moisture-resistant thermoplastic. Its letter designation is TW. It can operate at 140 degrees Fahrenheit maximum, and it can be used in wet or dry locations. It also tells us it's made of a flame-retardant, moisture-resistant thermoplastic. That's a pretty good summary of its insulation properties. You'd have all the information you needed here to make a decision regarding which type to choose. Many of the commonly used types of insulation are included on this chart. Okay, we'll get to the derating chart a little later on. At this point, let's concentrate on using the 2 charts we've just reviewed to select a conductor for a specific job. We'll say that we're required to connect a circuit that draws 40 amps of current at 480 volts AC. The location is damp, and the actual ambient temperature is approximately 85 degrees Fahrenheit. Oh, and let's specify that we'll use a copper conductor. That's the information we'll base our selection on. Now let's look at the allowable ampacities chart and see what type and size conductor we'll need to do the job. We'll start with ampacity. Going down this column, we find 40 amps. Looking to the left, in the size column, we see the size conductor we need is a number 8 AWG. We're using this first column because we want to use one of the insulation types listed above. They're the most common types, so they're usually readily available. Our next consideration is maximum operating temperature. But since the actual ambient at the work site is 85 degrees Fahrenheit, and we're not exceeding the conductor's allowable ampacity, we know we won't exceed the maximum operating temperature for this conductor. The next thing we need to consider is voltage. Remember, we have to insulate for peak voltages in AC circuits. To determine peak voltage for this circuit, we will multiply 480 volts times 1.414. This equals 679 volts. That means we have to insulate for a minimum of 679 volts. In this case, we will have to use a conductor insulated for 1,000 volts. So we check our conductor's markings to be sure it was rated at 1,000 volts. The last thing we need to consider is the environment. We said the location was damp. That means the insulation must be able to function in a wet location. Well, we saw earlier that TW can function in wet or dry locations. So we're ready to make a selection. A size 8 AWG type TW conductor rated at 1000 volts would do the job. Well, we've just used the allowable ampacities chart to select a conductor, but you must admit the conditions were ideal. Yet in your day-to-day work, you may have to install conductors in locations that are less than ideal. For example, you might have to install conductors in an area that's extremely hot. That's not all that uncommon in an industrial situation. So let's see what steps you'd have to take if the actual ambient temperature around the conductor at the installation site exceeds 86 degrees Fahrenheit. We'll stick with the situation we set up before, a circuit drawing 40 amps at 480 volts AC in a damp location. But this time, the actual ambient temperature surrounding the conductor will be 100 degrees Fahrenheit instead of 85 degrees Fahrenheit. We established that a size 8 AWG type TW conductor could carry 40 amps at a maximum operating temperature of 140 degrees Fahrenheit. And we noted that the internal temperature rise of that conductor with the maximum allowable current flowing through it would be 54 degrees Fahrenheit. Now, let's see what happens when we put that same conductor in at a location with an actual ambient temperature of 100 degrees Fahrenheit. Let's find out what its maximum operating temperature would be. We add the 54 degrees Fahrenheit internal temperature rise to the actual ambient of 100 degrees Fahrenheit, and we get 154 degrees Fahrenheit. Well, that exceeds the limit for this conductor. It can't carry 40 amps safely at 154 degrees Fahrenheit. What we need to do here is to derate the conductor. In other words, we have to determine how many amps it can safely carry at an ambient temperature of 100 degrees Fahrenheit. When you derate its ampacity, you're actually reducing its current carrying ability to match the needs of the environment. Here's a derating chart. It lists correction factors for ambient temperatures that exceed the established standard of 86 degrees Fahrenheit. The chart is set up this way. In the column on the far left, there's a list of temperatures given in degrees centigrade and Fahrenheit. Across the top, from left to right, are the maximum operating temperatures for the conductors. To use this chart, you look down the far left column until you've located the temperature that is equal to or exceeds the actual ambient temperature you're working with. Then, moving across from left to right, you locate the derating correction factor that's listed under the maximum operating temperature for your conductor. In this case, we're looking for the number nearest to our actual ambient temperature of 100 degrees Fahrenheit. Okay, now we'll move across the column till we get to 140 degrees Fahrenheit. That's the maximum operating temperature established for our conductor. Looking down, we see the derating correction factor is 0.82. To use this factor, we multiply it times the ampacity of the conductor. 0.82 times 40 amps equals 32.8 amps. That's how much current a size 8 AWG type TW conductor can safely carry in an actual ambient temperature of 100 degrees Fahrenheit. But what would you do if the circuit had to carry 40 amps? Well, actually, you have two options. You can use a conductor of the same size but having a higher maximum allowable operating temperature, or you can use a larger conductor, since for the same amount of current, a larger conductor will have a lower temperature rise. Let's start with option number one. Here on the allowable ampacities chart, we see that a size 8 AWG conductor with a maximum operating temperature of 167 degrees Fahrenheit can carry 50 amps. Now, we still have to derate that ampacity to reflect the actual ambient of 100 degrees Fahrenheit, right? So let's find the derating correction factor that's appropriate for this temperature limit. We'll use the same figure of 104 degrees Fahrenheit for actual ambient, but we'll look under the 167 degree Fahrenheit column for our correction factor. Okay, it says the factor we need is 0.88. We multiply 0.88 times 50 amps, and we see that with the upgraded insulation, a size 8 AWG can carry 44 amps in an actual ambient temperature of 100 degrees Fahrenheit. So this conductor could be used because its insulation allows it to function at a higher temperature. Now let's go back to the allowable ampacities chart again and see how increasing the size of the conductor affects its ampacity. This time we'll look under the 140 degree Fahrenheit listing and we'll move up from a size 8 AWG conductor to a size 6 AWG. It can carry 55 amps at 140 degrees Fahrenheit. Now, to derate this conductor, we go back to the original derating factor we used for the 140 degree Fahrenheit limit, which was 0.82. Okay, we multiply 55 amps times 0.82, and we find that a size 6 AWG type TW conductor can safely carry 45.1 amps in an actual ambient temperature of 100 degrees Fahrenheit. Your plant will probably have a preferred method of dealing with situations like this. It will also depend on what stock of conductors there is available for you to choose from. Well, we've covered a lot of information on how to select conductors. We've looked at some of the charts you'll be using most often, and we've dealt with some typical selection problems. Why don't you read over the material we've just talked about in your text? If you have any questions, be sure to clear them up with your instructor before we go on. Well, now you're familiar with the terminology used to describe conductors and to describe cables and some of the factors that have to be considered when you're selecting them. So let's go on to another aspect of our job as electricians. Let's go on to talk about some of the tasks that are frequently associated with conductors. In this segment, we'll concentrate on how to do a splice in a low-voltage system, and we'll look at the hardware that goes along with the task. A splice is a point at which two or more conductors are connected together to extend the overall length of the conductor, or a point at which two or more conductors branch out from a conductor. There are several kinds of devices used to connect the ends of conductors together within the splice. For simplicity's sake, we'll refer to these devices as connectors for the time being. Connectors usually fit into one of two categories: thermal connectors and mechanical connectors. Let's briefly discuss thermal connectors first. Although they're used in some circumstances, the National Electrical Code restricts their use in many situations. In addition to the restrictions applied by the code, there's another reason why thermal connectors are used less frequently than mechanical ones. Mechanical devices are easier to use, which means you can do a splice more quickly and efficiently with them. Thermal connectors use heat to make the connection between two conductors. One common method of making a thermal splice is to twist the ends of the conductors together and solder them. Now, this particular method requires no additional connecting device, but it will require insulation. Insulating splices is usually the final step in a splicing procedure, and it's usually done with electrical tape. However, some thermal connections do require special hardware that are used with solder to connect the ends of the conductors. Now, here's an example of a thermal lug. If you're familiar with lugs, you might expect to see a hole somewhere on the barrel of the lug. But on a thermal lug, a hole would allow solder to drip out of the barrel as it was applied. So one way to distinguish between a thermal lug and a mechanical lug is that you won't see a hole on the barrel of the thermal lug. Otherwise, the general construction may well be identical. Well, let's sum up what we've said about thermal connectors and thermal splices. Heat provides the means of joining the conductors together, and solder used alone or with a thermal lug are among the most common methods used to do a thermal splice. Let's go on to look at some mechanical connectors now. We'll concentrate on this type of connector because they're the ones you'll use most frequently in your day-to-day work. Mechanical connectors use mechanical pressure to join the ends of the conductors to the connector. Your primary objective whenever you're making a splice is to make sure that you've got a strong connection. It's got to be strong in two ways: mechanically strong and electrically strong. Now, here's an example of a mechanical connector that's frequently used to splice small conductors. It's a wire nut. It's one of the simplest connectors to put on. What you do is strip the insulation off the ends of the conductors and place the ends in here. Then you turn the wire nut until it's tight. Now, this type of a connector has an insulated shell. So once you've got it on tight, the splice is done. You don't need to add further insulation. Now, here's another mechanical connector called a sleeve. To make a splice using a sleeve, strip back the insulation a bit to ensure a good electrical connection within the sleeve, and then insert the ends of the conductors into the sleeve. After the conductors are in place, they're mechanically secured to the connector with a special tool called a crimper. You'll see how crimping is done later on in this segment. Now, this is another mechanical connector. With this type of device, the conductors are laid in the connector side by side and fastened in place as this nut is tightened. This is called a split bolt connector. Now, this connector is a mechanical lug. It's attached to the end of a conductor and crimped in place. Lugs can be used to connect two or more conductors together, and they can also be used to connect conductors to electrical equipment, with the exception of the first mechanical connector we saw, the wire nut. All of the other devices, the sleeve, the split bolt connector, and the mechanical lug, need to be insulated. Before we get into that part of the procedure, though, let's talk about the factors you have to consider when you're selecting a connector for a splice. You have to base your decision on two things: size and metal. The size of the conductors you're splicing together and the type of metal the conductors are made of. On most connectors, you'll see either a size or a range of sizes stamped on the metal. And in addition to that, you may find information that specifies the type of metal the device is suitable for. For example, you might see the letters AL, CU stamped on the connector. This would tell you that the device was suitable for a conductor that was made of either copper or aluminum. The designation of AL stands for aluminum and indicates that the connector should only be used on aluminum conductors. Anytime you come across a device that has no metal designation on it, restrict its use to copper conductors. Well, let's sum up what we've covered so far. We've talked about what a splice is, and we've looked at some typical connectors that you'll be using when you're making a splice. We've also gone over the factors you have to consider when you're selecting a connector for a particular application. Now it's time to take a look at the splicing procedure itself. We'll go over to the electrical shop in the plant for that. Bill's going to use a wire nut to make the first splice. The first step in the procedure is to strip the insulation off the ends of the conductors. He's using a stripper to do this. The amount of insulation he strips off is determined by the size of the wire nut. Now he places the ends of the conductors side by side and slips the wire nut on. He turns the wire nut until he sees the conductors start to twist a little. That tells him that the nut's on good and tight. The wire nut is insulated, so Bill doesn't have to do anything more. The splice is complete. Now Bill's going to be working with larger conductors. He's already chosen the sleeve he's going to use based on the two factors we mentioned, size and metal. He places the barrel of the sleeve next to the end of the conductor and puts his thumb where he'll start to strip. He'll use a knife to do the job this time because the conductors are so much bigger. He makes a 360-degree cut around the insulation at the mark. He has to be careful not to nick the metal of the conductor as he works. Then he splits the insulation and pulls it off. He'll do the same thing to the other conductor. To connect the sleeve to the ends of the conductors, he'll use a crimper. For conductors this size, he'll have to use a heavy-duty crimper in order to apply enough pressure to the sleeve to make a good, strong connection. Crimpers come in a variety of sizes, just as conductors and connectors do. You'll select your crimper according to the size of the hardware you choose. For really big splices, you might need to use a hydraulic crimper, but the hand-operated one is okay for this job. It happens to be adjustable, and it covers a range of sizes. Bill inserts the end of the conductor into one end of the sleeve. Then he places the sleeve into the jaw of the crimper. He makes sure the end of the sleeve is centered so the crimp will be just where he wants it. Then he squeezes the handles of the crimper together until they reach the stop point. Now he fastens the other end of the sleeve to the other conductor the same way. To complete the splice, Bill has to insulate it. He'll use electrical tape for this. The electrical tape will replace the insulation that was stripped off the conductors. Here's an example of the kind of information you'll see stamped on a conductor. This is marked 12, type TW, oil and moisture resistant, 600 volt. Well, when you go to replace this insulation, you'll want to be sure that the tape you use has the same qualities that the original insulation does. Electrical tape is usually rated for voltage and environment. These ratings are not stamped on the tape itself. They're usually printed on the box provided by the manufacturer. The tape Bill is using is rated according to VPM, volts per mil thickness. The box says that the tape can withstand 69,000 volts per mil thickness, and that far exceeds the voltage rating on the conductor, so the tape meets the voltage requirement. The information on the box also lists the types of insulation the tape can be used with. Bill is working with type TW, and that's on the list, so he can be sure the tape is compatible with the original insulation. Okay, Bill's going to tape the splice now. His objective is to tape the splice well enough to duplicate or exceed the quality of the original insulation. The tape has to provide strong electrical protection and mechanical protection when he's done. Bill will put at least 3 layers of tape on the splice. This will ensure that he surpasses the mechanical strength of the original insulation. He'll start in the center of the splice and then go out to about 1 inch beyond the insulation that remains on the conductor. Then he'll work his way back across the splice and out to 1 inch beyond the original insulation on the other conductor. He keeps a light tension on the tape as he works. Each time he lays a strip of tape, he overlaps the previous strip by about half its width. The light tension and the half lapping ensure 2 things. There won't be any air spaces between the layers, and the insulation will be mechanically strong. Okay, Bill's done taping and the splice is complete. Here are some partially completed splices. I've left the tape off so you could see the connectors. Here's the split bolt connector, and here are some lugs. They'd each have to be taped up before they could be used, of course. Well, we've covered a lot of information on splices done in low voltage applications. We've defined the term splice, and we've looked at the hardware and other equipment used to make a splice. We've talked about the factors you have to consider when you're choosing a connector and tape to do a splice. And we've looked at how a splice is done. Why don't you take some time now to read over all of this information in your text. If you have any questions pertaining to the procedure or other information, be sure you ask your instructor about them before we go on. Well, Bill's shown us how he does a splice. The next thing he's going to do is a pretty routine task for electricians. He's going to pick up a work order to put a motor into operation. Since this job is one that you'll be doing so often yourselves, we're going to follow Bill through all the steps involved. And they'll include something we haven't discussed yet, how to pull conductors through conduit. But that's practically the last thing we'll talk about. First things first. Let's look at the work order. It specifies that he's to run 3 12 AWG type TW conductors through 100 feet of conduit and connect up a motor. That means the first thing Bill has to do is go to the motor and check out the nameplate. He needs to verify that these conductors will do the job. In other words, he's going to make sure the size 12 conductors meet the amperage requirements and the voltage requirements. And he's going to have to check out the temperature and the location of the job site. Okay. What does the nameplate on the motor say? Well, it's a 2.68 amp, 440 volt, 3-phase AC motor. One look around the area tells him there's going to be moisture in the environment, and he'll have to allow for that. But as far as temperature is concerned, it won't exceed 86 degrees Fahrenheit or 30 degrees centigrade, so that won't present any difficulties. Okay, Bill can check his ampacity chart now to make sure number 12 AWG can carry 2.68 amps. To make his calculations, Bill will round this figure up to 3 amps. This is accepted practice, providing he doesn't go below 2.68 amps or he doesn't go above the next whole number. Well, it can carry 20 amps. That's far more than the required amount. but Bill will stick to what's stipulated on the work order. You see, the policy in his plant states that nothing smaller than a 12 AWG conductor can be used on a three-phase motor. Next, he considers the voltage requirement. All of the conductors on the chart are rated to withstand up to 2,000 volts, so there's no doubt that the 480 volts AC will be covered within the 0 to 2,000 volt range. The ambient temperature is below 86 degrees Fahrenheit, so the size 12 conductor is going to be fine in that respect too. What's left of the four basic requirements? Right, environment. The insulation has to be approved for a wet location. Well, we learned earlier that TW could be used in either wet or dry locations, and Bill's sure to have worked with it before, so he'll know that the type TW will do the job. All right, Bill's verified that the conductor specified in the work order meets the four requirements we talked about earlier. But in addition to those four, there are a couple of other factors Bill has to consider. One is the surge factor because he's working on a motor circuit, and the other is voltage drop. Voltage drop has to be considered because of the distance, 100 feet, that the conductors have to travel. Let's see what the surge factor involves first. Whenever you're hooking up a motor, you'll have to consider surge. Surge is the term that describes the additional amount of current that's needed to start the motor. Bill will use a standard figure to calculate the surge factor. He'll take 125% of the amp rating listed on the nameplate. 125% of 3 amps is about 4 amps. Now, the 12 AWG conductor is rated for 20 amps, so Bill knows that this size conductor can easily handle the current required to start the motor. Voltage drop is the next factor he has to consider. Anytime you're dealing with conductors that run a significant distance, like 100 feet, you'll have to consider voltage drop too. You see, as a conductor's length increases, its resistance to current flow is greater, and due to the increased resistance, you have a loss of voltage, or a voltage drop. Now, the amount of the voltage drop has to be kept within limits, and the limits are pretty much standard. Industry considers anything over 2% inefficient. So what Bill has to do is make sure that the conductor can still carry the amount of current the motor needs within a 2% voltage drop. Voltage drop is important because if the motor operates at less than its rated voltage, it'll operate inefficiently, and eventually other problems will occur. For example, the motor will overheat. So to make sure the voltage drop stays within 2%, Bill will check a voltage drop table. This is a portion of the table. The complete voltage drop table is in your text. This table gives the distance at which a given size conductor can carry a given amount of current within a 2% voltage drop. Now Bill's working with a three-phase circuit, but the voltage drop table gives the voltage drop for single-phase circuitry. To adapt the information for three-phase, we'll use another industrial standard. It's necessary to multiply the distance given for single-phase by 86.7%. When we get to that point, we'll round 86.7% to 86% and do the calculation. But first, we need to find 480 volts. Okay. The next thing we have to look for is 4 amps. 4 amps isn't listed, but 5 amps is. We can use 5 amps because it's a higher value than the 4 amps required by the motor. Also, 5 amps is the lowest value listed on this chart. It's generally acceptable when choosing a conductor to do a job to exceed the circuit requirement, but it's never acceptable to go below the circuit requirements. Okay, we'll move across the 5 amp column until we get to the distance in feet under the 12 AWG, the size of the conductor, 142 feet. So now we know that for single-phase circuitry, a size 12 AWG conductor can carry 5 amps a distance of 142 feet with a voltage drop of 2% or less. To adapt that information for three-phase circuitry, we have to take 86.7% of that number. We said we'd round it off, so we will. 86% of 142 feet is 122 feet. So for three-phase circuitry, a size 12 AWG can span a distance of 122 feet with a voltage drop of 2%. Since we know that the conductors Bill is working with will actually be spanning a distance of 100 feet, and the calculation was done for 5 amps, when even with the surge factor the motor will only draw 4 amps, there's no question that the size 12 AWG conductors can do the job. The motor will operate efficiently as far as its voltage requirement is concerned. Let's sum up quickly what Bill had to consider when he verified the conductor selection. First, he made sure the conductors met the amperage requirements and voltage requirements, and then the temperature and environmental requirements. After that, he considered the surge factor, and given the distance the conductors had to travel, the voltage drop. But Bill's only half done. There's still more checking to do. Now Bill has to deal with another aspect of the job. It has to do with the conduit. Conduit is a type of pipe electricians use to run conductors through. It provides good mechanical protection for the conductors. Now, there are rules in the code regarding how many conductors you can run through conduit. Bill has to check to be sure it's okay to run 3 size 12 AWG conductors through the conduit so far as the code's concerned. Bill knows it's 3/4 inch conduit, so he goes to a chart that tells the maximum number of conductors that are allowed in a given size conduit. This is a section of the chart. The complete chart is in your text. The conduit sizes are given at the top. On the left are the types of insulation and the sizes of the conductors. Okay, we found 3/4 inch. Now we need to find type TW and size 12 AWG. How many are allowed? According to this, we're well within the limit. 12 is the maximum, and we only need to run 3 conductors. Well, Bill's checked out all the facts he needs to know. He knows the conductors are okay for the job, and he knows the conduit can carry 3 conductors. Now he can begin the installation. Bill checks the electrical equipment to see if it's been de-energized. It's already been tagged out and the switch is off. Bill checks his voltage tester on an energized source to be sure it's working. Now he tests the circuit, phase to phase and phase to ground. Finally, he checks the voltage tester again to be sure it's in good working order. Okay, he knows it's safe, so he'll go on. Bill has to pull the conductors through the conduit. He'll use a fish tape to do it. The fish tape is a stiff wire that's usually contained in a plastic reel. First, Bill will run the fish tape through the conduit starting at the motor and work back through the conduit. That'll make the job of pulling the conductors through the conduit less difficult. It's easier to feed the conductors into the conduit downward, and it'll give him leverage when he pulls them out at the motor. Once he's got the fish tape through the conduit, the conductors will be fastened to the hook at the end of it. Rod, another electrician, is going to help Bill. He'll strip off a few inches of the insulation, then thread the conductors through the hook and fold them back. Then he'll tape the ends of the conductors in place. This will ensure that the conductors don't get separated from the hook, and it'll also help to make it easier to pull. Now, Rod's going to help Bill out by feeding the conductors into the conduit. This will keep the conductors from rubbing on the edge of the conduit, and it'll also help Bill as he pulls. It should be almost all the way through by now. Whenever you're pulling conductors through conduit, it's a good idea to leave a little extra length projecting from the conduit. Then, if for some reason you need an extra inch or two, you've got it. Okay, Bill's got what he needs. He unwraps the tape at the hook and straightens out his conductors. A little extra is left at this end, too. At this point, Bill's ready to hook up the motor. That'll involve terminations. We'll watch him do a termination in the next segment. But before we do, why don't you take some time to read over the material in your text on what we've just seen. Well, when we saw Bill last, he'd pulled the conductors through the conduit and had just finished disconnecting the fish tape. The next thing he's going to do is terminate those conductors to complete the circuit between the contactor that operates the motor and the motor itself. Before we go down into the plant to watch Bill finish up the job, though, let's talk about what a termination is. A termination is a stopping point for a conductor. It provides a means of connecting conductors to electrical equipment and completing a circuit. The devices used to do terminations are called terminators. Terminators can be divided into the same 2 general categories as our splice connectors, thermal and mechanical. When selecting a terminator to do a job, the same criteria apply to it as apply to a splice connector. In other words, the terminator must be made of the proper material and it must be the proper size. Now let's go back to the plant now and watch Bill as he does some terminations. He's already completed the first mechanical connection. We'll pick it up as he starts the second. The type of terminator he uses is a lug. He holds the lug up to the conductor to judge how much insulation should be stripped away. Then he strips it. He puts the lug on the end of the conductor and, using the crimping tool, crimps it, making sure the crimp is well centered on the lug. It's a good idea to give a test tug on the lug to make sure it's securely fastened to the conductor. Next, using the nut, bolt, and lock washers that are on the motor lead, he'll attach the lug to the lead and secure it with a spin-tight and a screwdriver. Once that's tight, Bill will complete the last mechanical connection the same way he did the first two. After the hardware is in place, Bill has to rebuild the insulation. This insulation will have to meet the same voltage requirements that the original insulation met. So Bill used the same selection process that he used when he chose the tape to rebuild the insulation around the splice. He considered voltage, temperature, and environment. Bill will put a minimum of 3 layers around the connection to ensure that the insulation will be both mechanically and electrically strong. He applies extra layers of tape around the end of the mechanical connection. This is done for mechanical protection so the metal edges of the motor housing won't cut and damage the termination. Bill keeps light tension on the tape as he works. The light tension on the tape prevents air spaces between the layers of tape and provides a strong electrical connection. Once he's finished rebuilding the insulation around this connection, he'll go on to insulate the other 2 mechanical connections using the same procedure. Well, you've just seen a typical termination procedure on a piece of low-voltage equipment. To complete the job, Bill has to terminate the remaining ends of the conductors to the contactor at the other end of the conduit. Before he starts those terminations, however, Bill is going to double-check to make sure that the contactor has been de-energized. You can see that the equipment's been tagged out. The switch is in the off position, and the fuses have been pulled. Using the same procedure as before, Bill will check the contactor with his voltage tester, phase to phase and phase to ground, to make sure it's de-energized. Once he knows it's safe to work on, he'll go on. Here, Bill's working with a set screw terminator. He measures the length of conductor he'll need to reach the set screw and snips off the rest. As before, he'll allow a little extra, in case he needs to go back to work on the circuit for another reason. Then he determines how much insulation he needs to strip and strips the insulation off. All he has to do now is insert the conductor into the slot and tighten down the screw to hold the conductor in place. Bill doesn't have to use tape to rebuild the insulation in this situation. Air serves as the insulator here due to the amount of space between the set screw terminators. Air is a good insulator. Looks like Bill's finished all 3 terminations. Now he'll test run the motor. The motor's running, and it's running in the right direction. Bill's finished as far as the work order is concerned. Why don't you read over what your text has to say on termination procedures and make sure you understand it completely. If you have any questions on the material in the last segment, be sure you bring them up with your instructor.